right where we left off with entanglement. So today we'll follow the exact same kind of schema as yesterday. Wong first, and then for a couple hours, and then a couple hours on assignment review. So entanglement is where we'll start. Go ahead and throw this in here. All right, perfect. So, so if a quantum state could be factored into a tensor product of individual qubit states, then it is not entangled. It is not entangled. So for example, with what they show us here, this is just two Hadamard states. Tensor product together. I don't know why I won't keep wanting to write that. 0 minus 1. So it's possible to check and see if we can factor any state by working through this example here. I worked through this one earlier today just to make sure I could get the mechanics down. So let's go ahead and jump in here. So let's say we have two arbitrary states, psi 1 and psi 2. Psi 1 is alpha sub 1 state 0 plus beta sub 1 state 1. And similarly, we have pi 2 is alpha sub 2. Or actually, sorry, let me use the convention that they use in the actual example here. Okay. 1 and 0. So 1, 1, 0, state 0, plus beta sub 0, state 1. So we have two different states with two different pairs of amplitudes. And let's say that we want to extrapolate these two psi's and psi 0 from some product state of two qubits, similar to similar to the one in the example. So we have this superposition of two qubits. And we want to see if we can pull this into two individual qubit states. If not, if it cannot be factored, by definition, it can be factored into product states, it's entangled. So usually, we can do some kind of visual inspection also to see if it's entangled. But officially, to know for certain, we can factor this. So let's see if we have any entanglement here. So when we have a product state, or when we have a tensor product where we're taking our alpha 1, beta 1, tensor producting with alpha 0, state 0, beta 0, state 1. And that gives us alpha 1, alpha 0, 0, 0, state 0, 0, plus alpha 1, beta 0, 0, 1, plus beta 1, alpha 0, state 1, 0, plus beta 1, beta sub 0, state 1, 1, just through distributing things through and getting our pairs together. So once we have this, we can take a look at our superposition. So we can see here, we can match up our states. So 0, 0 in our superposition has amplitude square root of 3 over 2 square roots of 2. Alpha 1 beta 0 has amplitude negative square root of 3 over 2 square roots of 2. 1, 0 has the amplitude of positive 1 alpha 0 of positive 1 over 2 square roots of 2, and beta 1 beta 0 has an amplitude of minus 1 over 2 square roots of 2. So now in order to solve, we just what is going on here? Alright, so in order to solve, we just follow an algebraic process. There we go. We just follow an algebraic process. So we can isolate, let's say in this example they put things into terms of, sorry, it's going down here. They put things into the terms of alpha sub 0. So alpha 1 is equivalent to square root of 3 over 2 square roots of 2 alpha sub 0. We just divide by alpha sub 0. Similarly here for beta sub 0, we'll solve for it in terms of a of 0, which is beta sub 0, pardon me, sorry. Beta sub 0 is in terms of goodness. Beta sub 0 is in terms of, sorry, I don't want to lose my train of thought here. Okay, so we take a look at this one. We know that beta sub 0 is equal to, first, minus square root of 3 over 2 square roots of 2 alpha 1. And we know that alpha 1 is equal to this. So we can bring that in here. Of 3, 2 square roots of 2 multiplied by square root of 3 over 2 square roots of 2 alpha 0, which winds up giving us, let's see, these 2 square roots of 2 will cancel out, and we'll be left with negative square root of 3 over square root of 3 over alpha sub 0. So we're going to flip and multiply here, reciprocate and multiply. So we wind up with minus square root of 3 alpha sub 0 over square root of 3, which gives us minus alpha 0, sub 0, pardon me. So, and I'll just collect these over here so we don't lose track of everything. A1 is square root of 3, 2 square roots of 2, alpha sub 0, beta 0 is equal to negative alpha sub 0. Next we can move on to beta sub 1, which is equal to beta sub 1 is equal to 1 over 2 square roots of 2 alpha sub 0. We just divide by alpha sub 0, move that over. And finally, we can go back in and plug things in and do some solve by substitution. So b of 1, we see right here that we have this fourth equation, beta sub 1, beta sub 0 is equal to this. So what we can do is we can solve for alpha sub 0 here by multiplying these out. So minus alpha sub 0 multiplied by 1 over 2 square root of 2 alpha sub 0 is equal to negative 1 over 2 square roots of 2. Distributing through, we get minus alpha 0 over 2 square roots of 2 alpha 0. And we wind up with minus 1 over 2 square roots of 2, which is equivalent. Now, we can actually just take this and plug this back into our back into our written out tensor product of our product states. So we got psi 1 and psi 0 is equal to square root of 3 over 2 square roots of 2 alpha sub 0, state 0, plus 1 over 2 square roots of 2, 1 alpha 0, multiplied by alpha 0 minus, or state 0, minus alpha 0, state 1. We can see that we can pull out this alpha sub 0 here and distribute it over. Excuse me. So what we wind up with in the final form is that we can factor our superposition into two product states, which are square root of 3, 2 square roots of 2, state 0, plus 1 over, sorry, I'm missing something here. Oh, that's right. I'll write it out like this, and then we can go over that last step with state 0 minus state 1. Both qubits need to be normalized. So here they just move the 1 square root of 2 over. Without the 1 square root of 2 here, these will be normalized with square root of 3 over 2 and 1 over 2. So we can pull out a 1 over square root of 2 and move it over to our right qubit. And we wind up with square root of 3, 2, state 0 plus 1 over 2, state 1. And 1 square root of 2 0 minus 1 square root of 2, 1. So this is minus on the right here. And this is just written as this. We can break that down into the final form of a tensor product. So some states cannot be factored into product states. If we look at the example that they give here, this is obviously, I mean, this is a Bell inequality state. This is a Bell state. So we want to, we know this is going to be entangled, but we can run it just by looking at it, but we can actually try to factor this out following what they've done here so we can see for sure. I mean, just visually you can tell that it doesn't matter which qubit is measured. It determines the other qubit. So if the first qubit is 0, then the second qubit will be 0. If the first qubit is 1, then the second qubit will be 1, and vice versa for the other way around. If we measure the second qubit first, we get 1. We know that this will be 1, and vice versa for the 0. So I won't necessarily write this out, but basically when they do the same process that we did up here, they wind up with some impossible situations. So either A1 or B sub 0 needs to be 0. But if A1 is 0, then this makes no sense. Then how can alpha sub 1, which would be 0 here, multiplied by alpha sub 0 equal this number? It would be 0. And if we set beta sub 0 to being 0, then this equation doesn't make any sense. We can't solve. So there's no solution when we try to factor these states. So this is entangled. So do you guys want to work through another example, or do you like one of these questions, or do you feel pretty confident on that? Okay. Like on the problem sets or anything like that with or the knowledge checks. Oh, in the lab. Okay. Okay. Yeah. No, there was a one that I got wrong on the lab that was really ticked me off that I'm looking forward to reviewing here later. Yeah, we can let's just take a look at let's just run through 4.11 really quick, just to show the process again. So we know, like I said, that we have two. We're trying to factor it into two psi 0 and psi 1. The combined weights for that are going to give us alpha 1 is 0. Just written a bunch of this. Oh, sorry. So alpha 1, alpha 0 for state 0, 0. Alpha sub 1, beta 0 for state 0, 1. Beta sub 1, alpha 0 for state 1, 0. And beta 1, beta 0 for state 1, 1. So our goal is to isolate and solve for these values based on what we have with our existing superposition. So here we have alpha 1, alpha 0, and so in this, the superposition they give us, which is 1 over square root of 2, state 0, 1 plus state 1, 0. So we can already kind of see here that we're going to have some zero amplitudes. So, for example, for 0, 0, we have a zero amplitude. The state in this superposition, this state does not exist. So alpha sub 1 times alpha sub 0 is 0. For alpha sub 1, beta sub 0, we have 1 over square root of 2. We have, 1 over square root of 2. For 1, 0, we have 1 over square root of 2. And then for beta 1, beta 0, which represents the amplitude for state 1, 1, it's also 0. So, immediately we can see the problem, right? If we start trying to isolate for a sub 0, so let's say that either, sorry, let me clarify that, a sub 0. Make sure, yes. So either a sub 1, or pardon me, either alpha sub 1 or alpha sub 0 could be equal to 0 here. And they would fulfill this equation, right? But if we just try that out, and so if alpha sub 1 is 0, well then how do we wind up with this value when we multiply by beta sub 0? It would be 0. Similarly with alpha sub 0, if that's 0, then how is multiplying by beta sub 1 giving us this float, this amplitude here, this non-zero amplitude? So therefore, there is no solution for this superposition. It cannot be factored. Cannot be factored into product states. And therefore, we have entanglement. With the second example, with B, so we have, for this, we have alpha sub 1, alpha 0 equivalent to, so 0, 0 once again is not present, so that's equal to 0. We have the amplitude for 0, 1 is 0. Beta 0 is equal to 0. Then we do have 1, 0. So the amplitude that results from multiplying the amplitudes of our I just wanted to say, I guess I really haven't mentioned this, but these are the respective amplitudes for the two states that we're trying to solve for. I don't know, I haven't mentioned that. I just wanted to clarify that just in case. So beta 1 and alpha 0 are equivalent to 1 over square root of 2. And then for 1, 1, which is beta sub 1, beta sub 0, it's equal to I over square root of 2. We'll just distribute this through. So great, let's try to solve here. So the possibility is, once again, we have a similar situation as before. Alpha 1 or alpha 0 could be 0. But unlike in the previous example, it actually works. Because if alpha sub 1 is 0, then this actually equates correctly. So we have 0 times beta sub 0, which gives us 0. So we're going to say that alpha sub 1 is 0, that this doesn't really help us solve for alpha sub 0 or beta sub 0 yet, but we can rewrite this in terms of, we can rewrite alpha sub 0 in terms of alpha sub 1. So alpha sub 0 is equal to 0 divided by Let me grab the textbook because I am going off script here just a little bit, I think. Grab my physical copy. 4.11. So yeah, so this can be factored. So I just confused something here for a second. Let me take this off. All right. So we can, if we put alpha 1 into terms of alpha 0, it's 0 over alpha 0. Similarly, if we put alpha sub 0 into terms of alpha sub 1, we wind up with 0 over alpha sub 1, which is just equal to 0 both times. But we know that this makes sense. So alpha sub 1 is 0. Question is that I kind of lost the track of is how does that help us actually isolate for beta sub 0 and everything else. So now I'm kind of getting confused myself here, because if in terms of alpha sub 1, the problem is that we have no way currently of discerning what this actually is. But let's just write it out and then bring it in and see if some things cancel out, etc. All right, so we have state 0. Just write this out here as put our framework. State 1, state 0, and state 1. So we know that this is 0. That alpha sub 1 is equal to 0, which means that this qubit is not in this, the first qubit is not in a superposition. It's in a single position of just state 1. And the second state is in, let's see, we need to solve for alpha 1, alpha 0 and beta 0. Pardon me? Right, it's beta 1. But my assumption is that because the amplitude for state 0 is 0, that the amplitude for B1 would be 1. Let's see, let me test that. Let's test that out and see if that works. So if beta 1 is 1, if essentially it's 100%, this qubit is not in the first qubit is not in superposition. It's just in state 1. Then that's the amplitude is 1. So that means that the amplitude for B sub 0 is simply I over square root of 2. And the amplitude for alpha sub 0 is just 1 over square root of 2. So 1 over square root of 2 and I over square root of 2. And let's verify that this is a superposition, or that this is normalized by taking the norm squares here. So that gives us 1/2 plus 1/2, which is 1. So the first qubit is in superposition with amplitude beta 1 being equal to 1. So it's not in superposition, it's just in state 1 with 100% probability. And then our second qubit is in a superposition with we could pull this 1 over square root of 2 out and just leave it in this form. So with 0 plus 0i state 1. That one's a little tricky. That one, let me verify. That seems copacetic, but let me just verify in the answers that that is indeed what they were looking for. Yes. So they just have it, they have it written. What is this? Nonsense. Okay. Let me move the pen away from the pad. Okay. So they just have it, they have it written as a product, as a tensor product of state 1, 1 over square root of 2, state 0, plus I state 1. Perfect. So that is not entangled, because we can factor it into these two product states. I would say, oh sorry, go ahead. Is I? Oh. Oh, okay. Oh, okay, gotcha. Okay, I can zoom in a little bit on the textbook, make it a bit larger as well, so we can see this a little better. Okay. So with state, so just the way that I like visually look at a superposition, we can, sometimes we have to do it the factoring way, and sometimes we can look at it just visually and take a look. I think Wong, or maybe there was something I read online, some third-party resource that talked about how to look at the different things, that the states that are available so 4.12, we can see visually that we have, so if we measure our first qubit and it's in state 0, it doesn't determine the value of the second qubit. So if we measure 0 on the first qubit, the second qubit can be either 0 or 1. Similarly, if we measure 1, then the other qubit can be either 0 or 1. So if we were seeing something where if we measured 0, the second qubit was the same state. So if it was 0 and it equated to 0, 1, similar to like what we saw up here with the first example. So when we had these two states, if it was 0, it had to be 1. And if the first qubit is 1, then the second qubit has to be 0. So these are not entangled. We could go through and prove that this can be factored out. But just visually, we can see that this is not entangled, purely because of the freedom that the second qubit has in determining what it is, regardless of measurement of the first. Conversely, on our second example here, we can actually work through this one. So this one is entangled. Let me just start a new whiteboard. This one is entangled, and I'll demonstrate. We can work through that one. So we have 1 over square root of 3, state 0, state 1, state plus. plus square root of 2 over 3, 1, state minus. So valid superposition, everything is normalized here. But let's see if we have a factorable product state or not. So we can do that by substituting in what we know about plus and minus. So we know that plus is 1 over square root of 2. 1 over square root of 2, 0 plus 1. And we know that minus is 1 over square root of 2, 0 minus 1. So we can distribute through and then figure out what we have. So 1 square root of 3 times square root of 2 over 0, 0 plus 0, 1 plus square root of 2/3 times 1 over square root of 2 times 1, 0 minus 1, 1. Come on. All right, we'll zoom out. Now, can we combine these in order to get something here? Well, let's say that we can combine this into one big superposition of 1 over square root of 2 1 over square root of 3, 0, 0 plus 1 over square root of 3, 0, 1 plus square root of 2/3, 1, 0 minus square root of 2/3. So sorry, that is minus 2/3 state 1, 1. So we need to do the same thing that we did before. So we're gonna analyze for alpha 1, alpha 0, alpha 1, beta. What is it? This is definitely something to put on the master note card. This little formula here, I think, is very valuable. Alpha 1, beta sub 0, beta sub 1, alpha sub 0, and beta sub 1, beta sub 0. And we know the amplitudes for each of these based here. So that's 1 over square root of 6, distributing through the two square roots there. 1 over square root of 6, 1 over square root of 6. I don't even know where to start with that one, so we'll just say 1 over square root of 2, square root of 2/3, and the same for here. And so we want to isolate and get our terms separated. Oh, it's 1 over square root of 2 times 1 over square root of 3. So yeah, just multiplying the two, multiplying our together there. So yeah, no worries. So now we need to isolate and try to solve. So similarly to before, we'll put things into terms of alpha sub 0. So alpha sub 1 is equivalent to 1 over square root of 6 alpha sub 0. Now we can come over here and plug this in and solve for beta sub 0 in terms of alpha sub 0. So we know that beta sub 0, we have 1 over square root of 6 alpha 0 times beta 0 equals 1 over square root of 6. Yes. So we can rewrite this here. Beta 0 over square root of 6 alpha 0. We can multiply by square root of 6 and multiply both sides by square root of 6 alpha 0 to eliminate. And we're left with beta sub 0 is equal to alpha sub 0. Okay, now we can move forward and solve for beta 1 in terms of alpha sub 0. And that's just equal to 1 over square root of 2 alpha 0 with square root of times square root of 2/3. So now we have enough to go and put things into our two formulae. So, and we can solve. So we've got, just going to leave a little bit more room here for the amplitudes. We have our two states here. We know that alpha 1 is equal to, alpha 1 is equal to 1 square root of 6 alpha, oh Lord, square root of 6 alpha sub 0. We know that b of 0, which is here, is equal to a of 0. We know that beta 1 is equal to 1 over, oh Lord, let's just, I'm going to need more space here, plus 1 over square root of 2 alpha 0 times square root of 2 over 3. And alpha 0 itself is equivalent to, we haven't isolated what this value is, but we can write it in here. So we can pull out alpha sub 0. So we're left with this on our second qubit. And then this alpha sub 0, we can distribute this through on this side. So this alpha sub 0, we pull it out of the right, we distribute it into the left, and so this comes through and it cancels out all the alpha sub 0s in these denominators. And so we're left with 1 over square root of 6, 0, plus 1 over square root of 2, square root of 2/3, 1. I'm sure there's a way to simplify that, but this is our factored product states. Let me verify that just in case I went off the rails here. This is 4.12a. Oh, that's right. So we need to, because this is not normalized, we have to do similar to what we did before. So we pull out a 1 square root of 2. pull out a 1 square root of 2 and oh, did I? Oh, yes. It is part B. How did I get beta 1? The P. Oh, okay. So I actually think that somewhere along the way I lost something in all this because according to the textbook, this is an entangled state. So I actually shouldn't have been able to factor this. So I think I played fast and loose with some of the algebra up here and made a mistake. Um, gotcha. Okay. So, so I'm looking here, and so the thing is that clearly I made a mistake somewhere, but let me just maybe it was something up here with the amplitudes, because algebraically, so I made a mistake somewhere, but all the algebra is correct. So if alpha 1 and alpha sub 0 are equal to 1 over square root of 6, then that means that alpha 1 in terms of alpha sub 0 is, 1 square root of 6 over square root of 6 alpha 0. When we take that and we plug it into beta 0, our thing here, so 1 square root of 6 has to equal beta 0 times 1 over square root of 6 alpha 0, which means we can pull this out here. So yeah, yeah, we can pull out 1 square root of 6 beta 0 over alpha 0 and have that equal to 1/6. So beta 0 over alpha 0 equals to 1, so beta 0 equals alpha 0. But I think at some point along the way when I was calculating these amplitudes, something went awry because this actually is not factorable according to the textbook. Maybe Wong is wrong. Maybe we just cracked the case, but I don't think so. So oh, the same factored state. Okay. Yeah, I don't know. Maybe this is an errata that should be flagged to the good people at Rooted Grove Publishing. I'll make a note of that over here to look and see if that one is actually like a mistake. Let me, in fact, I mean this ebook should be more up to date. So we're on page 150. Let me see what this says about 4.12. No, it says it's an entangled state. Yeah, I'm not sure. So typically, so this state here, this superposition is theoretically, well, not theoretically, actually, it's normalized because gives us 1/3 plus 2/3 equals 1. Now, when you pull in the phase, the global phase of 1 over square root of 2 that plays into these two Hadamard states of plus and minus, I'm not sure if that's what factors into the entanglement, but according to the textbook, it's the ability to not factorize, to not be factorizable, that makes it entangled. If we can't split. Okay, what do you got? Oh, here? Mm-hmm. Yeah, I have that here. I just pulled out the 1 over square root of 2 to make it global. Um, to make it global there. Yeah, I'm not sure. We can come back to this one later. I can ask the professor. I can make an Edson post and ask about it exactly. Um, but I'll leave, let me mark this one down as 4.12b. Okay. So we'll move into. I was hoping to, let's see what we got. We're gonna go into quantum gates. So when we are applying one qubit quantum gates to a single qubit, let's say that we have 2 qubits that are in state 0, 0, and we want to apply an H gate just to that guy, then we apply the tensor product of the two, H gate and the identity gate. So the H gate is going to work on the first qubit, and the identity gate will work on the second qubit. So it distributes through like so. H sub 0, tensor product of identity, state 0. So first qubit, second qubit. And it'll preserve this being just in state 0 with 0 with amplitude 1. And it'll put our first qubit into a superposition of 0 and 1. So we wind up with 1 over square root of 2 state 0 plus state 1 tensor product with state 0. That will distribute through, and what we wind up with is 1 over square root of 2 0, 0 plus 1, 0. So we can also rewrite that into, we can rewrite this into a column vector form of 1 over square root of 2. These two are equivalent of 1, 0, 1, 0, where this vector is just the total vector where we add up the Kronecker products of the two tensor products here. So we have 0, 0, that's equivalent to 0 tensor product 0. Since this is a vector 1, 0 and 1, 0, we take the Kronecker product, where we talked about this yesterday, where each element of the first vector is multiplied by the total second vector. So we get 1, 0, 0, 0 for that. And then for 1, 0, similarly, this is state 1, tensor product state 0. This is 0, 1 in column vector form, and 1, 0. So we wind up with taking the Kronecker product, and we wind up with 0, 0, 1, or yeah, 1, 0. Adding these two vectors together to get this, so we get our 1, 0, 1, 0. So this is of the column vector that encapsulates these two states. So this superposition in vector format is right here. The quantum circuits, we've all been dealing with that and seeing that in the labs. I don't think I need to necessarily mention like the notation that it has, but the they have some examples here. I recommend working through them just to see. In fact, let's just do this one just for example. It's the demonstration similar to that one, so that we just worked over. So we have H and H tensor product I. We're applying it to state 1, 0. Taking the tensor product of the two means that we want to apply the Hadamard gate to the first qubit and the identity gate to the second. We want to apply the identity gate to the second qubit. We want to preserve this qubit, and we want to put this into a superposition. So we wind up with, and in fact, we can let's bust this down even further and do this one as a matrix example. So we know that the Hadamard in matrix format is 1, 1, 1, 1, 1, negative 1, and state 1 is 0, 1. So we wind up with 1 over square root of 2, 0 plus 1, and 0 minus 1. One and negative 1. So that brings us down here to our Hadamard state of 0, 1 square root, 0 minus, oh Lord, that's not a square root, of state 1. Where, these are just our amplitudes, alpha and beta, for our various, our two states here. Similarly, the identity is going to preserve, we looked at this yesterday, but I'll just run through this one more time. Identity for this would just be 1, 0, 0, 1. We are in state 0. This is going to give us 1 times 0 plus 0 times 1, and 0 times 0 plus 1 times 1, which gives us 0 and 1, so it just preserves that. We wind up with 12 over 1, negative 1, 0, 1. This is going to be, a tensor product. So we will come in and do, this is square root of 2. We'll do our Kronecker product, 1 over square root of 2, 0, 1, and then 0, negative 1. So that's the superposition that results in, oh, actually, I got that backwards. Where did I go wrong here? So we put H into, which is 0 minus 1. Let's just work this out by hand here. So 1 over square root of 2, 0 minus 1 times 0, which winds up 1 over square root of 2, 0, 0, minus 1, 0, and gives us amplitudes of 1 for 0, 0, gives us amplitude of 0 right here, the second level here, for 0, 1. This state has 0 amplitude, so 1, 0, negative 1 for 1, 0, and 1, 1 has 0 amplitude, it's not present, so 0. Somehow, when I was taking my Kronecker product, oh, thank you for catching that. Yeah. So, sometimes I get the cart before the horse. So, we wind up with 1 times 1 times 0 times 0, 0 times 1, 1 times 0. So 1, 0. Boom. Kronecker product here of these two vectors. And we wind up with 1 times 1, 0 and negative 1 times 1, 0, or 1, 0, negative 1, 0. Perfect. 1 over square root of 2. So, that's the effect of applying a gate to just one qubit. If we want to apply a gate just to one qubit, we have to apply the identity gate to the other, so that it's not affected. So we can also just, if we wanted to skip doing them separately, what we can do is we can actually just calculate the tensor product of these two matrices together. So, and that way we have one big matrix that we can apply and do our calculations with instead of having to do them separately. It'll have the same effect when it's applied to, for example, 0, 0 or any other 2-qubit state. But we can just make one matrix that combines these two together. So as we mentioned, H is 1 over square root of 2, 1, 1, 1, and negative 1. I is our identity matrix, 1, 0, and 0, 1. We are taking the tensor product of these two. So this will be broken down as 1 over square root of 2, 1 times I'll just write our identity matrix. I'll just write I here for simplicity. 1 times I, 1 times I, and negative 1 times I, which results in 1 over square root of 2, 1, 0, 0, 1. Same thing here. We're just basically just bringing in our unchanged identity matrices. And then here, the ones are negated. So when we take this whole thing here, and we apply this to our superposition of, or not our two qubit state, let's say 1, 0, this will have the same effect as doing them separately. And we can look at that real quick. So let's say we have state 0, 1, and we want to apply this tensor product HI to this. So we want the H to be on the first and I to be on the second one. Instead of doing them separately, we're just going to use this big unified matrix that we made. So we wind up with 1 over square root of 2, 1, 0, 1, 0, 0, 1, 0, 1, 0, negative 1, 0, and 0, 1, 0, negative 1. Multiplied by the vector representation of this state, which is the Kronecker product of 0 and 1, which is just 0, 0, 1. It's just 0, 1, 0, 0. So to calculate, we want to multiply each row by each vector here and sum them up. So we wind up with I won't write everything out here, but basically we'll take this, multiply each individual term by its partner term here, and we wind up with 0. Similarly here, we'll wind up with 1 because everything else is 0. So 0 times 0 plus 1 times 1, etc., plus 0, 0, 0 times 1, so we wind up with 1. We wind up with, here we wind up with 0 as well. And here we wind up with 1. So in our operation, we have transformed this into this. So our final form here is 1 over square root of 2, 0, 1, plus 1, 1. And if we factor the 1 out, we see that this is in fact the Hadamard of 0 with the unchanged state 1. So we can do it via matrix forms. We can do it with the kind of the way they did it up here, where we know what happens when we apply it to the gate, so we do it sort of shorthand there with actually just writing out the kets. I prefer the matrix notation because pretty much you can solve any gate problem as long as you know the matrix representations. On my study sheet, I've got the matrix representations of every single gate and every all the 2-qubit and 3-qubit vectors states, so that I can just easily glance at those, and then if I see a sequence that I'm not familiar with, I can just really quickly calculate it actually with the matrix multiplication and the tensor product, so that you can solve pretty much any state. Similarly, let's say we're going to apply H and X to a 2-qubit state 0, 0. So we know that we can either apply these individually. So we can say, hey, H applied to this qubit that's in state 0, that is equal to 1 over square root of 2, state 0 plus state 1. So it puts the first qubit into superposition. We know that X flips the state. Well, it works by flipping the amplitudes. But considering that this is, so state 0 is just a superposition of state 0 with 1, with an amplitude of 1, a probability of 1, and a 0 for state 1. So we can simply flip those amplitudes through the X. So it's now state 1 with 1% probability. So state 1. Distributing things through, etc. You can solve that remaining superposition that way, or we can calculate the tensor product of the H and X matrices, and we can actually use a unified matrix to solve it that way. So H, again, 1 over square root of 2, 1, 1, 1, negative 1. We know that the poly X matrix is, oh Lord, I want to say, where did I write that down? It is, where is it? That's the right question. Where's that chart? Okay, there it is. 0, 1, 1, 0. So we could take this is the tensor product. We could take the Kronecker product here, 1 over square root of 2, 1 times the X matrix, 0, 1, 1, 0. Again here, 1 times there, the X matrix, and then here the 1s become negative. Okay. Perfect. So this is the tensor product of those two gates that we can then apply directly to our state. So let's say we have 0, 0. That's 1, 0, 0, 0 in column vector format. Similar to the way that we solved up there, we'll just take this and add it out. So 0 times 1 is 0, so we have all zeros up here. Here, there's only going to be 1. This is 1 times 1 plus all the rest of the products are zeros. Similarly, here we have 0, and then we also wind up with 1 here. So this is equivalent to 1 over square root of 2 of 0. We have no 0, 0 term, and we have no 1, 0 term. So it's 0, 1 plus 0, 1 plus 1, 1. pulling out the one term, we see that indeed this is pretty much the exact kind of same example here as the last one. We have applied the Hadamard to the 0, which puts it into this plus state, and it has the x has flipped the second qubit's 0 state into 1. Perfect. We can also, when we go over the labs and stuff, we'll actually dig into the Qiskit stuff and actually look at them visually. But here, this is just about notation. Pretty straightforward. So let's look at the 4.13. This one's a bit more involved, but it is useful. We've got the, sorry, 2 seconds. Okay, sorry about that, getting quite parched. So 4.13. Obviously, this is we have the Bell states, but we don't get into that until chapter 6, I believe. But so we have here. We'll just work through A just to show the principles here. So when we apply x to either qubit of this, then the result of, I don't even remember how to say this character. We'll call it the candelabra plus. When we apply an x to either qubit here, we'll get this thing plus up to a global phase. So they'll differ by a global phase, but a global phase is irrelevant, as global phases don't change the measurement outcomes. They don't change the amplitudes. So this one we've got, we've got 1 over square root of 2 state 0, 1, and 1, 0. And so we have an entangled 2-qubit state, 2-qubit superposition. So again, just visually, we can tell that it's entangled, because if it measures, the first qubit measures 0, then the second qubit must be 1. And if the first qubit is 0, then the second qubit must be, or first qubit is 1, then the second qubit must be 0. So we have 2 entangled qubits here. So when we apply an X gate to this superposition, regardless of which qubit we actually apply it to. So let's say that we are going to apply it to the first one, which gives us, we'll need a matrix form of X and I, which is here. Oh, okay. Gotcha. So let's just really quick, we can take xi and I tensor product x. So this is applying x applying x to first qubit, and this is applying x to the second qubit, and identity, identity to the first, well, to the second in that one, to the second qubit. So let's go ahead and let's get our matrix form here. So x, as we know, what we just saw was 1, 0, 0, 1, or pardon me, 0, 1, 1, 0. Identity is 1, 0, 0, 1. We're doing the Kronecker product. So we've got 0 times our identity matrix, so that's going to be all zeros. 1 times our identity matrix, that'll be 1, 0, 0, 1. One times our identity matrix will give us 1, 0, 0, 1. And then again, all zeros here. So that's what x and x on the first and I on the second looks like in matrix form. We'll also solve for, come on, okay, go over there. All right. So we have, again, the identity matrix this time, tensor product with x. That's 1, 0. We wind up with 0, 1, 1, 0. All zeros here, all zeros here, and 0, 1, 1, 0. So these are the two matrix forms of these two gate sequences. And now we can test them against our superposition to see what's cooking, so to speak. Let me zoom out a little bit so we can work with this here. So for our xi example, first let's get the vector form of the superposition. So we have no 0, 0 or 1, 1. So we know that the amplitudes for those are going to be 0. And the amplitudes for 0, 1 and 1, 0 are equal. They're both 1 over square root of 2. So we can apply our matrix here to this column vector. Okay. Apply this to our column vector and solve this with matrix multiplication. So I'll do this longhand so we can, so 0 times 0 plus 0 times 1 over square root of 2 plus 1 times 1 square root of 2 plus 0 times 0. We've got 0 times 0 plus 0 times 1 over square root of 2 plus 0 times 1 over square root of 2 plus 1 times 0. And down here we've got 1 times 0 plus 0 times 1 over square root of 2 plus 0 times 1 over square root of 2 plus 0 times 0. And for our last one, we've got 0 times 0 plus 1 times 1 over square root of 2 plus 1 over square root of 2 times 0 plus 0 times 0. And that all adds up to 1 over square root of 2, 0, 0, 1 over square root of 2. Which gives us, we can extrapolate the amplitudes for our states here. This is 0, 0, this is 0, 1, this is 1, 0, and this is 1, 1. So our new superposition is 1 over square root of 2, 0, 0, plus 1, 1. And that is, as the example wants us to see, as the question is telling us, that is the same thing as here. So applying the x gate to either qubit of candelabra 1 gives us this 1. I really should probably start to learn what these are actually called. But yeah, so we could do it the other way as well, just to see. I don't necessarily think that is going to be. I don't think that's necessary for us to work through that as well. It's the same process. So we would take this and we would multiply it by our same thing here, and we would wind up with the exact same vector. So 1 over square root of 2, 0, 0, 1 over square root of 2. That's a square root of 2. It looks like Picasso, but there we go. It looks even worse now. Whatever. So pretty much when the x gate is applied to either of those, it shifts into a different superposition. It shifts in between these the Bell states, the classic set of entangled states that we'll find out more about later. We already worked through 4.14 basically, because we already looked at H tensor product X as a 4x4 matrix earlier, and I'd like to move on, if everyone's okay, into 2-qubit quantum gates. Or do you want to see another example like with B here? All right, perfect. I'll move on into 2-qubit quantum gates. So we have several different gates that work with more than one qubit. 2 or 3, I believe, is what we'll see in this section. So the C0, the controlled knot, flips the right qubit if the left qubit is 1. So we have our states here. So the left qubit is 0, so it does not affect that. So this state passes through the gate and comes out as 0, 0. But if we have, for any case, 1 here in the left, or so let's say 1, 0, then the control qubit flips our target. It activates and flips our target. So we wind up with 1, 0, and 1, 1 for these two states once they pass through the C0 gate. So the target bit here, our right qubit, becomes the XOR of the two. So we can look at that here. So let's say we're taking the C0 of 1, 0. That is equivalent to 1 and the XOR of 1 and 0. So this equates to 1. So we see the C0 gate, first one's 1, it flips it to 1. And similarly, if this were 1, then we would have 1 XOR 1, which would flip this to 0 in our final form. So it's a quantum XOR gate, basically. Not basically, it is a quantum XOR gate. So another name for the C0 is the CX. That's what Qiskit calls it, the CX gate. So that's the controlled X gate, the controlled NOT gate. Basically flipping the amplitude if the control is 1. It can also act on a superposition. So, as an example here, let's just say we have this one here with these arbitrary amplitudes, C sub 0 and C sub 1, etc. C sub 2, 1, 0, plus C sub 3, 1, 1. If we put a C0 gate over this superposition, onto the superposition, then the C0 distributes through, so to each of these 2-qubit states. And the result is that we wind up with C0, 0, 0. So this one's unchanged. The control qubit is 0. C1 is unchanged. The amplitude for state 0, 1 is unchanged. The left qubit is not 1. However, it switches these two. The X gate switches the amplitudes. So 1, 0, once we apply the C0 gate, becomes 1, 1. So it now has C3, or pardon me, C2, actually I got ahead of myself here, C2, 1, 1. This becomes 1, 0, and so this 1, 0 now has amplitude C3. In a matrix form, C0 is 1, 0, 0, 0, 1, 0, 0. So this is representative of 0, 0. This is representative of 0, 1, 1, 0, and 1, 1. So 0, 0, 0, 1, 0. So they flip the amplitudes here. Otherwise, this would just be an identity matrix, right? It would preserve all the amplitudes. But here, these two amplitudes are flipped. So let's look at the actual gate representation here. You know, you have there we go. That's the C0 in the actual drawing there. We've all worked with that quite a fair bit in the labs, etc. So I'm not going to really hammer on about the actual representations in the actual visual representations. We can also add. We can flip a control by assessing Hadamard gates. Before measurement, or before we reach our C0 gate. So we have a control qubit set to 1, and sorry, where are we? Right, so we have 0 and 0. It goes through, becomes an equal superposition. This also becomes an equal superposition of 1, 2, 0, plus 1. We assess the half the time. It'll be 1. The left qubit will be 1. Half the time it'll be 1/2 of time. The left qubit will be 1. The other half it'll be 0. So 50% of the time it'll flip the state. and then 50% of the time it won't. Then we apply another Hadamard to get things back into their original format. And voila, we are back at we have achieved our C0. So 2 Hadamard rotations are an identity matrix. So by wedging this C0 in here, we put both of these into equal superpositions. Then we assess our C0, which half the time it'll become 1, half the time it'll become 0. And then we apply another H to put things back, and then we have our unified state at the end. So they have it written here as that these two are equivalent. So applying a C0 to a 0, 0 is the same thing as applying a C0 to a 0, 1. In other words, taking this and turning it into this guy right here. We can go into this incredibly long longhand proof of this circuit identity, but I would just write this down on the note sheet. I don't think they would ask us to. I just think knowing this might give you like a quick answer. Lakshmi did say we might see things directly from this textbook in, or even directly from the practice problems in the textbook. So I like to, I'm going to fill this sheet back and front in the most minuscule handwriting ever and just have a jeweler's loop on if I have to. But I think that these circuit identities are useful to have written down, and this just proves that that this is true. So instead of doing it the long form way, they say, of course, using linear algebra is easier. So they break it down into the matrix form with the C0 of sub 0, 1 state here, and bringing it through in the linear algebra way, in the matrix multiplication, we wind up in the exact same spot with this. So I'm not going to work through that unless you guys absolutely want me to. The example is here for you to look through, but these two are in fact equivalent. So the C0 gate, and this is something that will really come into play in the next chapter, or not the next chapter, but chapter 6, which is the next, because chapter 5 is basically extraneous, or vestigial rather. So C0 can produce entanglement. It can produce entanglement because we can apply it to a two-state system, a 2-qubit system, and entangle the two. So, for example, we have C0 of plus and 0. That is C0 of, let's bring this out here, of 1 square root of 2, 0 plus square root of 1. Square root, or state 0, which gives us C0 of 1 over square root of 2 of 0, 0, and 1, 0. Oof, butchered that. Distributing that C0 through, we wind up with 1 over square root of 2 C0 of 0, 0 plus C0 of 1, 0. Nothing happens here because 0, the left qubit is 0. Here, however, it turns this into 1, 1. And so we wind up with this entangled state. So we went from 2 qubits, one which had its own 100% zero state, and one which had a superposition. These were individual. So we could measure either one of these, and they would not affect the outcome of the either. So if this is equal 0 or 0, so we could say half the time when we measure the first qubit, it'll be 0. This doesn't affect the second qubit. If we measure the second qubit first, it'll be 0, but it doesn't affect the measurement of the second qubit because there's still an equal. It doesn't collapse this, and it doesn't push it to be anything. We still have an equal probability of being 0 or 1 for our next measured qubit. However, once we apply the C0 to this, we wind up with a superposition, where if the first one is 0, the second one has to be 0. If the first one is 1, the second one has to be 1. So something that we'll look into is, C0 is part of the universal gate set because it can do that. The universal gate set has some various things that have to be true about it in order to be universal. It has to be able to create superpositions. It has to be able to create entanglement. It has to be able to deal with complex numbers. So C0 is part of the universal gate set because it can produce entanglement. It can operate on multiple qubits. So single qubit gates cannot produce entanglement. Only gates that work on multiple qubits. So even something like, okay, well, we say, well, what about the Hadamard? What if we put both qubits into superposition, right? And then wouldn't that, but it's still, the fact remains that even if we put 2 qubits into superposition with the Hadamard, each with a Hadamard gate, they have their own individual states. Say these are both 0. Now we'll have 4 different probabilities of getting 0, 0, 0, 1, 1, 0, etc. But there's no entanglement there. They each can be measured and not affect the outcome of the other. So Hadamard gates can create superposition, which is important for being able to build other gates from, being a universal gate, but they cannot create entanglement. So we have to use C0s in our universal set to prove that. We can take a look at one of these circuit identities. Let's look at D, because we haven't used Z gates today. We covered them a fair amount yesterday, but we have yet to mess around with the Z gate. So Z gate or Z gate, I sometimes use those interchangeably. Z gates have matrix form of 1, 0, 0, and -1. When applied to a state 0, they do nothing. They maintain the amplitude. When they're applied to state 1, they negate the amplitude for state 1. So a Z gate has that matrix form, and of course our identity is 1, 0, 0, 1. And C0, the matrix form of C0 is, where are you, guy? C0 is 1, 0, 0, 0, 0, 1, 0. Basically the identity matrix, but with the last 2 elements transposed. The last little 2x2 block transposed. So we want to prove this circuit identity that, where are we? Okay. That the C0 of the tensor product of gate I and gate Z is equivalent to the tensor product of gate Z with gate Z, and then a C0. So we want to look at the sequence. So first we'll take our tensor, so for the left-hand side, C naught of I tensor Z. We'll take our tensor product, which is our Kronecker product. So we have the 1 multiplied by the Z matrix, so 1, 0, 0, negative 1. 0 times the Kronecker matrix is 0, or times the Z matrix is 0. Similarly here, and then here, we would have, again, 1, 0, 0, negative 1. So we're going to apply the C naught to this. We're going to use this matrix. So a little bit involved here, but we've got 0, 0, 1, 0, 0. 0, 0, 0, 1, and 0, 0, 1, 0. We're going to multiply these together, these two matrices. So we will take the sum of each of the rows times the individual columns here. So this sequence times this guy will be right here. We're going to wind up with 1. Because 1 times 1 is 1. Everything else is going to be a 0. So that sums to 1. The second value here will be 0. Third value here will be 0 as well, and 0 as well. For our other 12 values, we'll just follow the same schema. 0, minus 1, 0, minus 1, 0, 0, 0, 0. Sorry, 0, where are we at here? Third value to there. 0. No, sorry. That's not a 0. That is a 1. Yes, that's a 1. Okay. Similarly, 0 and 0 here. Negative 1. Because we've got this guy times this, which gives us negative 1. Negative 1 times 1 plus all the rest are going to be 0 times 0. Negative 1 and 0. So this is the result of applying a C naught to the tensor product of an identity and Z gate. Similarly over here, if we take Z, Z, that's going to be the Kronecker product of two Z matrices. So write that out as basically 1 times the Z, so 1, 0, 0, negative 1. Zeros all here, zeros all here, and negative 1, 0, 0, negative, or positive 1, pardon me. Perfect. So we'll multiply these together, and we'll wind up with the exact same thing that we have here. So 1. I mean, we can just pretty much go ahead and write these two out. Sorry, 2, 1, 0, negative 1, 0. So we know that the C naught gate is not going to affect our two leftmost columns. So 1, 0, 0, 0, 0. However, it's going to affect the two amplitudes here. So we'll bring in the third value for this guy is going to be 0, 0, negative 1, 0. Boom, which is 0. The fourth value here will be, oh, I apologize, 2 seconds, guys. Oh, sorry about that. Wife headed off to the ICU for the night shift. Okay, sorry. The fourth value here is our third, so times our fourth column, which is -1. This is 1, this is 0. That's bass-ackwards. Sorry. These two should be equivalent. Okay. Just got a little confused over there. So 0, and then our fourth column, our fourth row, sorry, times the first column. Yes, there we go. 1. And then third column, or third row times fourth column is -1 here. Okay, so we have proved this identity through finding equivalent matrix forms. So C0 of the tensor product of the identity and the z-gate is equivalent to finding the tensor product of a z-gate and a z-gate and then multiplying it by a C0 gate. Okay. So we didn't really have to use, I don't really think we've used this one in any of our examples yet in class projects, but the anti-controlled NOT gate, it's the same thing as it's just a cool gate, I think. Anti-C0 is the opposite of the C0. So instead of flipping on 1, it flips on 0. So if the control qubit is 0. And that's, I'm pretty sure you can do that in Qiskit by itself. The open dot is the anti-control there. But you can also do it with doing X's on a C0. Again, it's we can just show that. I worked through this example today, and I like this one. So we say anti-C0, and then X, C0, X, and qubit 1, qubit 2, 0, 0, 0, 1, 1, 0, 1, 1. So the anti-qubit would turn this into 0 and 1. Let's say, it's the left one is the control, the right one is the target, and this would turn it into 0, 0. No effect with the anti-qubit here because our left is 1. So with here, when we apply the X gate to our control qubit, our first qubit, sorry, this is Q1, this is Q2. So we apply, in this example, we apply Q1, or X to our first qubit, which is 0, flips it into a 1. Then we pass through the C0. So now 1, this is just a normal C0. So this is 1, so it'll flip Q2 into 1. And then we flip Q1 back to a 0. So we get the Q1 equals 0. So we wind up getting the exact same state, 0 and 1, as these two are equivalent. We can use surrounding X's to emulate an anti-C0. I won't go through these examples here, but they follow this exact same schema. So 4.18 is pretty heavy, but I'm not sure if we have time for that one. I'll earmark this one to come back to and look at. I just want to get through the rest of these gates. So controlled U, the CU gate, exact same thing. If the control is 1, it operates on the target. So on 1, 0. This is equivalent to state 1 Cu of 0. This is 1. The Cu is now going to come in and operate on that second qubit. The matrix form of C and U. So let's say U is a 2 by 2 matrix of A, B, C, and D. Oh, A, B, C, and D. Then first two columns will be normal because they'll be 0, and thus nothing will happen. But when we get down here into our 1, 0 and 1, 1, it will impact the second qubit by applying this U matrix. And again, U could be a rotation. It could be a number of things, which we'll look at in some of the examples. Controlled Z, exact same principle. We apply Z conditioned on the state of a control, and the same thing with the S. So any gate can be controlled. So, for example, let's say, what is the controlled Z gate as a matrix? So just an example to see what that one, how we would kind of think through putting that one into matrix form. Well, we know that Z normally is 1, 0, 0, negative 1. So it does not affect the first one. It does affect the second one. So not C, not Z, sorry. CZ, control Z. So these two will be fine. They won't do anything to these. However, if they are, then it will apply a Z. Let me double check that. Bam, yeah. So once we get to 1, 0 and 1, 1, well, that's when things get a little funky. So it will assess a Z gate onto the second qubit. So the second qubit is 0 here. It'll leave the amplitude as it is with this 1, 0, right? And then here it'll negate the amplitude of state 1 into a negative. Swap gate. This we went over this in the knowledge check actually yesterday, where basically if we can swap the amplitudes of 2 qubits. So 0, 0, not a great example, but that equals 0, 0. If we want to swap 0, 1, that'll become 1, 0, and vice versa for the other two. It does not produce entanglement because if we are able to swap them, then they are in product state. So if the qubits are in a product state, swapping the factors results in a product state. So it can act on the superposition. So all that it does when applied to this arbitrary superposition with C's for our amplitudes is that it will swap these two. As 0, 1 becomes 1, 0 after the swap, and 1, 0 becomes 0, 1, these two will switch places. So we will wind up going from C0, C1, C2, and C3 as our amplitudes column vector to C0, C1, or pardon me, C2, C1, C3. So 0, 1, 1, 0. We can build a swap circuit. Oh, actually, sorry, I should give you the juice, the real juice, which is swap as a matrix form. So 1, 0. So we can see here it just swaps these middle two. So 1, 0 and 0, 1. Or, sorry, 0, 1 and 1, 0. When we apply this to our amplitudes, these we would find that these have been swapped. Yeah, so you can see once you multiply it by the original, multiply this matrix by the original amplitude vector, it just switches these middle two around. This is often drawn as this, or like this thing. We walked through the C0 example yesterday, but you can run through that with a truth table if you want to. But 3 C0s conditioned on the first qubit, then the second qubit, then the first qubit again, will swap the states for 0, 1, and 1, 0. You can also prove it as 3 C0 matrix multipliers here. The middle being a C0 0, 1 specifically, and it equates to the matrix that we saw earlier, which is the swap. Real quick, let's just work through this example, or one of the examples. So let's just look at A. So when we apply swap to this superposition, swap of 1/2 0, 0 minus 0, 1 plus 1, 0 plus 1, 1. So they want us to show that we get W3. So we could do this various ways. We could do it with the linear algebra way. We could break this into a column vector of amplitudes, right? We could say 1/2, 1/2, negative 1/2, 1/2, and 1/2. And we could bring it in and multiply it with our swap matrix, and we could show that these two will switch places. But we already know that these two are going to switch places, so we can just simply rewrite it as 1/2. State 0, 0 and state 1, 1 are unaffected. So this becomes plus 0, 1, and this becomes minus 1, 0, which is equivalent to W3, as they say here. Is everyone good on swap gates, or do we need to do another example? All right, cool. We'll move on. Toffoli gate. Toffoli gate is a 3-qubit gate. So it operates, it's a controlled NOT gate, CC NOT. You might see that as well. And it operates on 3-qubit systems, flipping them if the left two are 1. So it can't be either or. It's not an XOR situation. They both have to be. So for example, Toffoli of 1, 0, 1 will wind up as 1, 0, 1. Similarly with 1, 1, 1, we get 0, 1, 1. They both have both of the control bits have to be 1 in order to flip our third bit. So 1, 1, 1 will equate to state 1, 1, 0. And vice versa. If this were 0, this would turn into 1, 1, 1. It's the, so as they show down there, Toffoli of ABC is equivalent to A, B, and then the XOR of A and B XOR C. So A and B XOR C. So, we had 1, 0, 1, 1 and 0. The AND of that is 0. C was 1. The original third qubit here was 1. So 0 XOR 1 is 1. So C stays the same. But if we have 1 and 1 here, then 1 and 1 is 1. XORed with C being 1 gives us 0. And similarly, 1 XOR 0 gives us 1. So it's just the XOR of the A and B with C. And this one has a gnarly matrix. I really, frankly, don't want to write this out. But it's a 64. It's an 8 by 8. Because we have it's a 2 to the third by 2 to the third matrix for each possible state of the 3 qubits involved. And visually, we just have this thing here. The 2 controls that we condition upon, and then our target. Control and control. So this one says just do the matrix. Okay, I'm not going to worry about 4.23 because that one is just like the CNOT gate. We can have an anti-Toffoli gate. The anti-Toffoli gate operates if the control bit is 0. Or 1 or plus or whatever basis state we're in. The 4.24. Oh yeah. So it turns 0, 0, 0, for example, into 0, 0, 1, and vice versa. Zero, zero, zero. So it's just conditioned on the first 2 qubits being 0. I'm not going to draw out the anti-Toffoli as a matrix. You guys can do that if you would like, but as far as I'm aware, I don't think we've really used that one. The no cloning. Hello. The no cloning theorem. So if we have in a classical sense, if we have a bit and we want to copy the information from it, it's deterministic, right? It's either 0 or it's 1. We can read it and then we can move that data over to a new location, just zap it in there. But with qubits, we're in superpositions most of the time, right? So if we measure it, well, it collapses. And we neither A, learn the initial superposition, and furthermore, we don't learn the superposition, and furthermore, once we measure the qubit we're trying to copy, it collapses, losing the superstate there, the superposition there. So it's a lose-lose situation to try to copy an unknown. So this applies to qubits where the superposition is unknown, right? If we know the qubit, right? So if I say, hey, as it says, if they use an example here, if I say we have a qubit in the superposition state plus, right? We can copy that. So we could say that here they have the tensor product of an identity and an H gate. So we just maintain we start off with a 0 second bit, and we would wind up with plus and plus. But if it's unknown, it's impossible, because we can't do it without observing it. And once we observe it, it changes it, and we have no way of recovering what it was before. So that's pretty straightforward. I don't think they're gonna quiz us as hardcore as like asking us to prove it using linear algebra. But basically, the way to prove it is we know that if we have some gate that can copy this state psi onto some arbitrary qubit 0, that's it, we just start in state 0, then that would be equivalent to psi tensor product psi, and they break it down algebraically and with their Kronecker products. And so basically, in order to solve for what this gate should be, we need to know the initial. So in order to construct a gate U that copies, a qubit in state psi, just whatever arbitrary state it is, whatever arbitrary state it is in, we would actually first need to know the amplitudes alpha and beta for the qubit that we are trying to copy. So again, it's an unknown qubit, so we have no idea about these qubits and that are about these amplitudes. And so that's what this is essentially proving, is that there's no way to solve this equality or these equations without understanding alpha and beta first. Let's see. Yeah, quantum adders, the fun stuff. This is part of the first lab, I believe. How much? Let's see. We've got quantum adders and universal gates. We can skip error correction in chapter 4 because we don't start that until next week. Pretty sure that's the last part of this chapter. Okay, so we'll finish up chapter 4 really quickly by looking at the quantum adder and then the universal gates, and then we'll move into the assignment reviews. And I'll just zip through this since we all implemented this in the lab. I personally struggle with this one because I tried to do it. Well, we'll get into that, but as we were discussing on day 1, your classical adder can be applied ripple wise. So we get the sum and we pass out the carry, and we just ripple down through there, and then until we get our final sum. It's just a series of full adders, right? For however many binary number pairs, right? We would need 3 of these guys for a 3-digit binary addition. However, the problem is that the full adder in classical full adder is not. Classical full adder is not reversible. And in order to be a quantum gate, in order for the full adder to be a valid quantum gate, it has to be reversible. So we bring in these 2 ancilla bits, as they're called, ancillary bits. And after we get our full adder, we take the sum and the carryout, and we XOR those with these ancillary bits, right? So these are just initialized to 0, and we come through and XOR these guys so that we can have actual, this comes down here with E and gets XOR'd, right? And the sum, which I need to draw a little further out. Carryout comes to E. Oh, Lord. Carryout comes to E. Sum and D come together into an XOR. And that way, when we look at that's the way we can actually reverse the gate. We can tell what the input was based on the output, thanks to these ancillary bits, these ancilla. And the way that breaks down then is that we need 5 inputs for each full adder. We need our C in, our carry in, our A, B, D, and E, and we're going to output. Again, we have to output the same that we put in, so that they can. It's just one of those. I'm not really sure why that's a rule, but S XORed with D, and our C out XORed with E, and with here, and now we can put all these together into a ripple. There are alternative ways to do this. We can replace the logic gates with NAND gates. There's a bunch of different discussions about more efficient ways to do it. These are reversible forms of the classic gates that we have. So X is reversible because no matter what we put in, no matter what comes out, we can tell what went in. If it's a 1, we know it was state 0. If it's 0, we knew it was in state 1. To Foley gate, we can tell that as well. Right, we have 2 qubits, 0, 0, 0, 1, 1, 0, 1, 1. We would output A and B, and then A and B. 1, 0, 0. So this is fully reversible because for each distinctive output, we have a distinctive input. The same thing with, so all these gates are reversible. And then we get into the actual implementation with the full adder, which I'm not going to go into because we'll go over that in the lab. To do quantum sum. Yeah, the quantum sum is just implemented using 2 CNOTs, and the carry is implemented using a CNOT and 2 Toffoli's. So we'll see that in the lab. And then we string them together into... This is the one that I tried to build for the lab, and I had some troubles with this because I was forgetting to reset my ancilla bits. So they would, by the time they got here and started to reverse, the ancillas were still holding the values that had been assigned over here. So let's just scroll. Circuit complexity, not exactly sure if they're going to quiz us on this, but basically how many gates are involved. So with the full adder is composed of a certain number of gates. The The quantum ripple carry adder used that they implement in the book has 4n minus 2 Toffoli gates and 4n gates or C0 gates. C0 gates. So this is so we have n, right? We have n pairs of numbers in the addition, right? So for that n, we needed 4n minus 2 Toffolis and 4n C0 gates. So this is a linear relationship, right? Essentially, if we were doing this as big O, we would say, you know, oh, well, they have it here, of n in terms of circuit complexity. So it's efficient. Adding in superposition, not really sure if they're going to quiz us on this. I didn't spend a lot of time on this. I'll make a note to look at that a little later, personally. Universal quantum gates. I think this is the last part of this chapter. Okay. So universal quantum gates, as I was mentioning earlier, in order to be a universal, well, sorry, what is a universal quantum gate to begin with, right? It is, universal quantum gates are the sets of gates with which we can build all other gates. So in order to have that, right, so in order to be able to essentially build any type of quantum gate that we need, there are three things that need to be taken into consideration. One, we need to be able to generate superpositions. We need to be able to create entanglement. And we need to be able to work with complex amplitudes. So let's think about why each of these is essential, right? We have qubits. Qubits are not deterministic. They are in superpositions. So if we have for example, take a C0 gate, right? A C0 gate can alter states, but it can't create superpositions. If I apply C0 to 1, it creates 0. If I apply C0 to a series of qubits, all it's going to do is change the state that they're in, but it's not going to put them into a superposition where they have different probabilities of being. A Hadamard gate can do that, right? A Hadamard gate can put 0 into an equal, 1/2 probability of being in 0 or 1. And the same thing for 1. So superpositions are necessary for quantum operations. So therefore, in order to be part of the universal gate set, a gate within the set, not necessarily all the gates within a set, because essentially all the gates will work together in the universal set will work together to create the quantum gates that we need. So not every gate needs to have all three of these, but they all work in tandem. So superpositions, right? The H gate can create superpositions. We need to have entanglement. Now that's where the C0 gate comes in. We saw from our earlier example when we applied C0 to plus and 0 that we wound up with this with one of the Bell states, right? We wound up with one of the primary entangled states, and the C0 can do that, but Hadamard can't. Hadamard can put things into superpositions, but it can't actually entangle qubits. So we need something like the C0 gate to actually cause entanglement between two individual qubits. And furthermore, we need the ability to handle complex amplitudes. Amplitudes can be either real or complex. So there are gates like the C naught and the H that work with real numbers, but they don't work with complex amplitudes. So we need to have a gate that can do that. So something like the Z gate, right, that assesses a rotation with EI pi to the 4. It's able to work with complex amplitudes because it contains an imaginary component within the gate. So, for example, they talk about how the C naught, H gate, and S is not universal. We cannot build every other quantum gate out of a combination of these three because the S gate does not deal with complex amplitudes. The little terminology here. So the set of gates that can be generated by a set of other gates is the Clifford group. Again, I don't know how important this is, but I like the obscure terms. I like to bring them out at dinner parties. I'm just kidding. I haven't been to a dinner party in like a decade. The set. So the gates that can be generated by a set are Clifford group, and the set of gates itself that generates the Clifford group is therefore, what do you know, a Clifford group generator. So a universal quantum gate, by definition, should be able to generate more than the Clifford group, right? So be able to be generated, we should be able to generate essentially an infinite number of quantum gates. If a quantum gate exists and we haven't found it yet, when we find it, we should be able to build it with this universal quantum gate. So if we look at 4.33, right, we've got a Toffoli, an H, and a Z gate. So the problem with that is that neither of those can create superpositions. Fairly certain. I think I wrote this down. Hang on. 4.33. 4.33. Oh, wait, sorry, yeah. The Toffoli gate can cause entanglement because it operates on multiple qubits. But what we're missing here is the ability to... Actually, this was wrong. It's not the Z gate, it's the T gate. The T gate deals with that phase. The Z gate is an 180-degree rotation. So this one, the Toffoli, H, and Z gate set, has no way of interacting with complex amplitudes. Therefore, it's not a universal gate set. All of these, they cannot create entanglement. These are all single qubit states, single qubit gates. And we need something that operates on multiple qubits in order to create entanglement. And then C, again, we're missing the element that can create entanglement. Swap can swap around amplitudes, but it actually can't combine qubits in a way that creates entanglement. And these others, even though H gives us superposition, and we cannot generate entanglement with this set. So some examples of universal gate sets, we can use a C naught with any single qubit gate. To create any other gate. Because we can combine C naught with single qubit gates to create superpositions. We can build a Hadamard with a combination of a C naught and other single qubit gates, like rotational gates, like our S's and our Y's, etc., with the rotation gates. So as you see there, like a C naught, an R gate, a rotational gate, and an S is universal. We can build any quantum gate for that through this. The C naught, H, and T. C naught gives us entanglement, H gives us superposition, T allows us to work with complex amplitudes. Therefore, these three can build any gate. H plus any 2-qubit unitary gate. And we discussed yesterday, all quantum gates have to be unitary, which means that if there's a quantum gate U, it needs to have an inverse. And in Gates terms, if it has an inverse, that's U dagger, which is its conjugate transpose. So if a quantum gate has to be unitary, and that means that its conjugate itself times its conjugate transpose equals the identity matrix. So if there's any U gate that's unitary, that passes the check, right, that is valid, that involves 2 qubits, a multi-qubit gate there, we can team up with an H gate and we can create any quantum gate that we need. Complexity without numbers. Not really sure how important this is. We really didn't discuss this at all. Controlled Hadamard, Toffoli with any. These are just other examples of universal quantum gate sets that don't necessarily need to interact with complex amplitudes, because we can rewrite any complex amplitude, which is z equals x plus iy, where x is the real part and y is the imaginary part. We can just express this as any two real numbers, x, y, and then just we have not done any of that in this course, so I don't expect that they're going to expect us. I don't expect that they want us to go, that we're going to have to go that deep on the exam. Quantum error correction, we're going to skip over that because we don't start that until, next week in the course. Quantum programming, cool chapter, but honestly, complete dead weight in this book. I skimmed over it in 10 minutes or so. I prefer, if you guys are interested, just libgen the, where is it? Libgen the, do I have it here? Libgen the Qiskit Pocket Guide. It's like a complete overview of how to do pretty much any circuit thing you need in Qiskit. It's like 200 pages PDF. Very cool. I found that much more useful than reading this chapter in Wong. So yeah, perfect. I think that's a good place to stop with the Wong coverage. And even though I'm pretty sure we have some entanglement stuff on the first assignment, or on the first problem set, I'm going to stop the recording because we're going to go into class specific assignments. And just like yesterday and the day before, I'll put the first